Hello again. So we saw some examples in our last video where we saw that some events can affect the probability of other events. And we did a few calculations of those probabilities, those new probabilities, given that some event had already occurred. So we want to just give some definitions and look at a special formula right now. So the official definition is as follows. A conditional probability is the probability of an event occurring given that another event has already occurred. And we use this notation, the probability of B/A, as to read the probability of B given A. That is, what's the probability of B given that A has already occurred. In terms of diagrams and calculations, we can do this. Assuming that all outcomes are equally likely, we can do it this way. If S is our sample space, and this first circle is A and this circle is B, because we're given A has occurred, we only care about the outcomes in A. So we can, instead of considering the whole sample space, we'll limit our interest to A. And then the only way that B can happen is if these outcomes in this intersection occur. Okay. So the conditional probability of B given A is really the number of outcomes in this set divided by the number of outcomes in this whole set. So that's what this is. This reads the size of A and B divided by the size of A. This absolute value, remember, that just means the size of whatever set is inside. And we can take this and we can divide by the number of outcomes in the sample space, S, and then we get this divided by this, but this is just the usual probability of A and B, and this is the usual probability of A. So we get the conditional probability of B given A is equal to the probability of A and B divided by the probability of A. And if we multiply both sides by the probability of A, we get this equation. The probability of A and B is equal to the probability of A times the probability of B given A. So this is called the multiplication rule, or the multiplication principle. It's really just this equation and this equation basically say the same thing. And sometimes you can use this to compute the conditional probability, or sometimes you want to find the probability of A and B. Maybe it's not quite as easy as you think, but it's easy to compute the conditional probability. So then you can use this form. Basically, the way you want to do this is whatever's easier for you. But like in the previous example with the things in the jar, it was just easier to compute this directly. One example, if we go back to the previous example where we had the jars and the balls, okay, we basically computed the probability of B given A. We computed what's the probability that the second ball is green given the first ball is green. So that was in this situation. If the first ball we removed was green, then this was our situation, and we have a 2/5 chance of getting that. So getting a green ball. So we said that this was 2/5. And then what was the probability of A and B happening? Well, we can use the multiplication principle now. And the probability of A and B, that is the first ball being green and the second ball being green, is this. We have the probability of A, we know that's 1/2. We just computed the probability of B given A is 2/5. We multiply these together and we get 2/10, which reduces to 1/5. Okay. All right, so that's one way where we might want to use this multiplication principle. Another example, if we skip ahead to our last page in our notes, where we have here we have a table where we're given it's a list of all information about the employees in the company and whether they contribute or don't contribute to their retirement accounts. And here the information is broken down into male and female employees. So in this company, we have an equal number of males and females, right? And then this tells you of those males and females, how many contribute, how many don't contribute. So if a person was chosen at random from this company, what would be the probability that that person contributes, given that that person's a male? Well, this tells us that we're only interested in males, so we are just looking at this information. There are 250 males, out of which 116 contribute. So this would be 116 over 250. Okay, where this 250 comes from this number here. Given that they're female, well, the probability that they contribute given they're female, we have 250 females, out of which 143 contribute. So the probability here would be 143. Now, switching this around, what's the probability that the person is female, given that they contribute? Well, now if we look at we're interested in just the people who contribute, and there are 259 of them that contribute, and 143 are female. So this would be 143 out of 259. What's the probability that they're male, given that they don't contribute? Well, there are 241 that don't contribute, and of those 241, 134 are male. So this would be 134 divided by 241. And then the last probability is not really a probability, it's just what's the probability that person is male and doesn't contribute. And when you have enough information here, you don't have to go and use the formula. You can just go and say, well, here we are, this is what we want. That 134 people don't contribute and are male, and this is the total number of employees is 500, right? So the probability that they're male and don't contribute is 134 out of 500. Okay, so that's how conditional probabilities work. We'll talk about in the next part. We will talk about go back to talking about independence of events. So, okay.